So now we're going to form our familiar portfolio of long-short positions. So what we're going to do is the same calculation we did in the prior module for that impossible bond pricing model. And in fact, what we're going to do here is to develop the same portfolio and determine what it tells us if we require that no arbitrage be possible. So in the prior example, we had a fixed model, and we showed that it had arbitrage. Here we have a model where we have some flexibility, and we're going to ask the question, if we require that arbitrage is impossible, what does that tell us about the model? What constriction or what restrictions does that make on prices and the model? So we're going to form, as usual, a portfolio with a bond maturity T2. We're going to have N, and N should typically be negative because it's going to be a hedge position. We're going to have N bonds with a maturity of T1. We're going to have our cash position of W. We're then going to just simply apply the earlier formula for the differential of I, recalling that the differential of W is always RW dt because it's a risk-free asset. You'll notice that we then have the differential for the T2 function, the differential for the T1 function. We're going to do a little bit of algebra here. And in order to make it risk-free, we have an expression which looks somewhat familiar from the earlier work. And it's quite obvious what we need to do. If we look at this expression, we have a variety of dt terms in the DI expression. We don't care about those. Those are the drift term. It's really this collection of terms that we're trying to get rid of. That's where the risk is. So the question becomes, how do we get rid of those terms? And you can see there has to be a relationship between the QP value at time T2 and N times the QP value at time T1. And indeed, the algebra says that N is negative, this ratio. And notice that if we just go back and look at the definition of Q, that N is basically a ratio of R derivatives. So this is reminiscent of a delta-based hedging, that PR is the derivative, the rate of change of the price function when R changes. And here we're using a hedge ratio that's a ratio of those R derivatives. And this is very reminiscent of what we would be doing in a stock model, whereby in our stock model we're looking at a ratio of deltas. If we were trying to hedge one stock position with another, we would use a ratio of deltas to tell us how many positions to take. Now for this value of N, the portfolio is going to be risk-free because that was the design. We eliminate the DZ terms, and so because it's risk-free, it must be that DI is equal to R times I dt, right? That was the idea, that if we have a portfolio that is risk-free, its differential must be the risk-free rate with a time adjustment. So if we just now equate DI with that given value of N to R times I times dt, and we do some algebra, we get this formula. That for each of the two bonds, the expression alpha minus R over Q is constant. It's independent of the term of the bond. Well, this looks like a Sharpe ratio. Formally, to be a Sharpe ratio, I should put a negative in the denominator, because you remember we have those negatives in the definition of Q. The Sharpe ratio is the ratio of the return minus the risk-free rate, the excess return, divided by the volatility of that return. And because we have a negative in front of Q in our expression, it's really minus Q. That's the volatility. So the Sharpe ratio has a minus in the Q. And what this says is that in order for this to be this portfolio to give me a return of the risk-free bond, which it must because it's risk-free, in order for that to happen, every bond must have the same Sharpe ratio. This is reminiscent of some earlier work we did where we saw that if securities are perfectly correlated, they must have the same Sharpe ratio. Well, indeed, our bonds are perfectly correlated because they're all driven by the same DZ. And so this generalizes that earlier result